We define compactness as follows. So a subset K in X is compact. We defined as if every open cover has a finite subcover. Every open cover has an open subcover, finite subcover. That is, if K is contained in union of 0 to alpha, all these things are open subset of X. Okay. Then there exists alpha 1 up to alpha n in the indexing set. Okay, you can choose finitely many of them such that K is actually contained in. Okay. So this is the definition of compactness. This is in essence, a generalization of finiteness, what we see. Okay, but you don't see it as of course every finite set will satisfy this, but okay. So why we need this kind of, so this is a purely topological definition. It's just use openness. It does not need metric space. But we will derive equivalent condition for a metric space. You should remember it need not be true in general topological space. Okay? So some of the, we will be using some definition like totally boundedness, using even boundedness, using open ball and all that. That may not be true. That may not, that may not make sense in a topological space. Something like sequentially compact we will be proving, and that is not true in general topological space. Even some few things like it needs to be Hausdorff for it to be closed and all that. A compact set is closed and all. So we have already noticed this corollary, a compact. Incidentally, you can, if you want to define the whole space is compact, then this will be equality. You can instead define this compactness using restricting the metric to K itself and considering that as a metric space. And you can use that. You can take open sets in K with respect to the relative topology and define this. It will all work the same. So from K contained in X is compact or X is compact, then it is separable. We notice that because separability is equivalent to having every open cover as a countable subcover, we indeed have finite subcover. So this is separable. Now we want to prove the following. We want to see the properties of compactness. First, the proposition. If K is compact, K is contained in some metric space, or this is a metric space, doesn't matter. And suppose F contained in K is closed, is a closed subset, then F is also compact. Also compact. Proof. The proof is very simple. You have to, if there is an open cover for this, you have to find a finite subcover. But if complement is open, you can add that to open cover and that will cover K. That will have a finite subcover, and you can get a finite subcover for this from that. Okay. So let F contained in U alpha, union of U alpha, open cover. Okay. Then K is contained in F complement, union this. This is union, not U. Alpha mi U alpha. Okay. Then this is a finite subcover. That finite subcover may contain, may not contain F complement. If it doesn't contain, doesn't matter. If it covers K, it will cover F also. If it contains this, if it contains F complement, then you can remove the F complement and the remaining open subsets will cover F, because you can prove that. This contain, if X is there, then it cannot be in the F complement, so it has to be one of them. You can prove it. Okay. Then, so there exists finite subcover. Whether F complement is there or not doesn't matter. Finite subcover for K, and from that get a finite subcover. Okay, I have orally said it. That it's a trivial sentence, right? Okay, get a finite subcover for F from that. Okay, so it's done. Now let's prove the most important property of compact set. compact. This implies K is closed and bounded. Any compact subset is closed and bounded. If it is for a general X, of course, every whole metric space is closed. For general, we will prove that it is actually complete. Okay, we'll come to the complete is slightly different from closed, of course. Okay. Okay. So it's a subset of a metric space, then it is closed, we want to prove. Okay. So bounded is clear. Bounded is, what is bounded? Exact definition. I mean, it should be clear, but let's write it. A subset K contained, a subset A contained in X is bounded if there exists a single open ball such that B of XM, big open ball which contains A. That's all. Okay. So now we want to prove it is bounded. Now you take, let X in, take any X in K, then B of X N, as N grows, at some point it has to contain everything, right? Union of N equal to 1 to infinity. This certainly contains K. This contains X also. This certainly contains K. So now get a finite subcover. Subcover, I mean, we will have something like that. Bxn1 up to Bx, yeah, and K, whatever, doesn't matter. Choose the maximum of this. Okay. Maximum of N1 up to N. Okay. Then that B of Xn will contain all the bigger one will contain the smaller one, and B of Xn contains K. So it's bounded is clear. Okay. So we want to prove closeness. So to prove K is closed. So what do you have to prove? To prove K is closed, if there is a sequence in K which converges to something, it converges to some element, then that element has to be there. So every limit point in our definition has to be in K. Okay. Or, I mean, that's one thing, one way. Or, we want to say every limit point is in every limit or point of K is in K. That's what we want to prove. That is, we want to prove that a limit point cannot be in K complement. Okay. So on the contrary, suppose X is in K complement and X is a limit point, K closure, and also X is in closure. Okay. That is for all N. That means every open ball, that is for all R greater than 0, BXR intersection K is not empty. Okay, that's what it means, right? That's what it means by a limit point, right? Okay, there is a sequence converging to that, and this can be, you can take this as the original definition of the limit point. You take any open ball around XR, okay, that should intersect K. That's what it means by limit point, by definition. Okay. Okay. Now, Hausdorff property, we have proved a Hausdorff property. Hausdorffness implies there exists for any y, any fixed y in K, there exists uy. I mean, you can take open ball if you want. Okay, and then I have to write so many things. So I'm taking open set uy, which has y. This is the element of this, and vy. This open set depends on y. That's why I'm calling it vy, which has x, such that uy intersection vy is empty, right? This is the Hausdorff property. If you have 2 points in a metric space, they are not different. They are different. So y is in K and x is in K complement, so they have to be different. Okay, so there exists open sets around x and around y around x, okay, which you call uy and vy, such that this is equal to empty. Okay, this happens for each y. Okay, now union of y in K, uy equal to contains K. Okay, compactness implies there exists y1 up to yn such that union of uyi I equal to 1 to n. This contains K. Okay. Now, Vyi intersection Uyi is empty. Okay. This implies intersection of Vyi to n. This will not intersect with any of intersection of Uyi, Uij is empty. Intersection will be empty. Each one does not intersect with one of them. The intersection will not intersect with any one of them, right? Because something is here, it has to be in everything. So that will not be in one of them. So it will not be, it will not intersect with all of them. So I can write union. Union of Vyi, sorry, Uyi, this is Uyi equal to empty. This is empty. So these two sets are disjoint. Okay. Now this is an open set, right? We call it V. This intersection of finitely many open set. V is open and X is in V, and V intersection K is contains this equal to empty. This is a contradiction to the fact that this. Okay. This contradicts. This is my symbol for contradiction. This is a contradiction to V X is Y X is a limit point. Okay. This contradiction to the fact that X is a limit point. X is in the closure. So we assume the contrary and it is not true. So this implies K is closed. Done. Any questions? Anyway, if you have any questions in all the previous classes and other thing, you can ask me anytime, before the class or after the class, okay? Or any day, especially on the day we have class 2 to 3, you can come to my room and also ask, okay? If you have any serious question. I mean, you should sort it out yourself. If you have any serious question, you can come. Okay, I will try to, as far as possible, I will do. If I don't know, I cannot. Okay? Not every question I will answer. Okay, so we want to see whether the converse is also true. The converse need not be true. It is true in finite dimensional vector space. We'll do for finite dimensional vector space later, maybe in the next class. But for Rn, it will be clear today, mostly. I mean, if I prove one proposition, it will be clear. But in general, it is not true. Example. So that is why we need to define like that. Otherwise, we can define compactness as closed and bounded. Bounded, closed, and bounded, we can define. But when the dimension is infinite, when you have a vector space, and the dimension is in the general topological space, in the general metric space, when the dimension is infinite, then this is not true. Okay? Example, let X is equal to L1. Okay? L1 sequences absolutely summable. Okay? Absolutely summable. Then the closed ball X bar in L1, such that norm of X bar 1. This is a sequence. Okay, this is a sequence like this. Okay. Norm of X1 bar equal to less than or equal to 1, or equal to 1 is also fine. Is closed. Of course, it is bounded. It's contained in the ball slightly bigger than 1. To take a radius slightly bigger than 1, it is bounded, of course. Okay, so this is closed and bounded, but this is not compact. So I will come back to this. To prove this is not compact, you can work with open set. But I will prove it the other way using what is called sequentially compact. Okay. So I will prove this. We will prove it again later, but I will give you one proof now. I will come back to that. So definition. K contained in X is sequentially compact. This is same as compact for metric spaces, but for the time being, this definition. Okay. Sequentially compact. If for all, I mean, it's usually, if you take any infinite subset, that should have a limit point, which is same as this. Okay. For all xn contained in K, okay, there exists a subsequence. For all sequence, there exists a subsequence xn k, k equal to 1 to infinity, such that xn k converges to some x, which is in K. Every sequence should have a convergent subsequence. Okay. This is like Bolzano-Weierstrass theorem. So this is the definition of sequentially compactness. Okay. Now we prove the following. K is compact implies K is sequentially compact. Proof is actually very easy. So let, suppose not. So you want to prove it's sequentially compact. Suppose it's not sequentially compact. Okay. Then there exists a sequence xn contained in K such that no subsequence converges. That's what it means. Okay. Then what happens? Now let F is equal to just this sequence. I mean, see, this is a misuse of notation. If you take light sequence like this, it's like a set. But Excel, I mean, in a set, we don't repeat elements, right? But in a sequence, it may repeat or something. It may not be different or something. This is not, this is sequence. We're just indexing by natural number and writing it. This is a misuse of notation. This is sequence. This is set, okay? Okay, you take all in Excel such that you may repeat and then call it set. Okay? This has, you collected all those Excel. Then this is closed. Why is it closed? By definition, if you take a sequence from this set, okay, what does it mean? Let me orally explain, because I'm going to prove again the sequentially compact. Let me not give, I orally say, and it should be convincing. Okay, if you take a subsequence of this, I mean, if not a subsequence, if you take a sequence from this set, okay, which converges, it's possible. It need not, but if it is a subsequence, it will not converge. Subsequence means there is infinitely many elements. It will not be convergent. But if there is a sequence from this set, then its infinite subsequence will not converge. So finite set has to repeat on its own, right? But then finites from, if you take a sequence from a finite set, it converges only if it's constant after some time. Okay. So if we have some other yk contained in this set converges, then convince yourself, then this yk is eventually constant. That's what it means. It's constant after some time. Okay. It's a constant sequence after n. Yeah.
Here's some sequence.
Yeah.
In the set.
Yes.
Now you are getting any sequence.
Yeah, you're taking any sequence from that set. Okay. So yeah, tell me.
So the new sequence may be in different order.
It can be in any order. What I'm saying is, if it comes from some infinitely many of them, that will give a subsequence of them. You are saying any order.
Yeah, that may not be subsequent of the previous.
That is true, but Converging means after some time it will be less than something. So we can arrange it to get a subsequence, right? If you think about it, it will be a subsequence, right? It is convergent. You are saying it's convergent sequence. So after some time, it has to be Cauchy. Distance between them should be less than something, right? It should be Cauchy, for example. I mean, I haven't defined Cauchy, but you can define it using the same metric you can define. Okay?
And you go on like that.
Yeah,
higher and higher.
you can get a subsequence out of it somehow. Okay? So that it is in the, yeah, you can index it in such a way so that you get a subsequence. Think about it. This thing, we don't want to spend time on this. Okay, I will screw it again. Okay, for the time being. Okay. So but unless it is a finite set, you will be able to find a subsequence of this sequence. Right? Good question, but it's true. Okay. So only a finite set you have to get a sequence from a finite set to get a convergent sequence, which should be eventually constant if it is convergent. Okay. So this is a closed subset. So F is compact. But since this does not have a convergent subsequence, okay, there exists Rn greater than 0 such that B of x Rn intersection all those xn, okay, with n all those xm with n minus this n, okay, is empty, right? It will not contain, except that it, right? This is a, otherwise it will be convergent, no? Okay. So otherwise it will have a convergent subsequence, right? So there should be an open ball around each xn such that it does not intersect with any of the sequence, right? So this is possible. But then this bxn Rn, bxn Rn, bxn for R, sorry, bxn Rn does not intersect with, does not contain any of the xn other than xn. Okay, that's what I have written here. Yeah. So bxn Rn, this union contains, of course, this xn. Okay. But this is compact. This does not have any, does not have finite subset. Finite subset. Okay. So contradiction. So it should be sequentially compact. Okay. Now let's come to that. So I want to prove that, I want to give a counter example for any closed and bounded set need not be compact in infinite M. So L1 is a vector space and it's a metric space, it's an armed space, it's a metric space. And you take the closed ball of radius 1, okay, which is of course bounded. It's a closed ball, any closed ball is closed, right? Any closed ball is, because the norm is continuous or metric is continuous, it's the inverse image of 0, 1, closed interval 0, 1, right? Okay, so it's closed, okay, with respect to the metric. Since the metric is continuous, this is open. I mean, you can otherwise also you can prove that it is closed. So this is a closed and bounded set, okay, and you consider this En, this sequence, 0 up to 1 and 0, 0, 0 everywhere, okay, at the nth place. Okay. En. This has norm 1, right? It's a summation. The norm is the summation of all the elements. So norm of En equal to 1. So En is in that, you call it B. En is in B. But I want to prove that this does not have a subsequence which converges, because norm of En minus Em equal to, this will differ. I mean, it will be 0 everywhere except nth place. This is 0 everywhere except nth place. So when n not equal to m, this will differ in the nth place and mth place. So there you will sum 1. So it will be 2. This is 1 now. It will be 2. Okay, clear? Okay, so it is 2. So there is a fixed distance between any two elements. Okay, it cannot have a, I mean, it should be Cauchy. The distance between them should shrink and it should go to 0. Okay. So this is not En, does not have any convergence subsequence. You can in fact prove any infinite dimensional vector space. You can do that. We will. Okay, we will see another example. So we will prove a theorem for compact subsets of C01 with supranorm, which is called Arzelà-Ascoli theorem. So I will not deal with that. I will give this as an exercise. You take C01 with the L1 norm. The norm F1 equal to integral mod F0 to 1. Okay. F is from functions from to complex number. Okay. Then you consider this INX, this function. N can be in Z. Okay. So this does not have a subsequence you can prove. This is contained in ball of radius 1, all those F with norm F1 equal to 1. Okay. You can compute the norms. You can compute the take F2, better F2. This is exercise. I mean, you just compute this now. Square. I take the F2 norm. It's for some reason. Okay, it's better to do F2 norm. It will be easy. Okay. E to the power of n. X is the variable. N is a number. It's a sequence of functions, right? Each Fn equal to E Fnx e power nx. I is square root of -1, of course. Okay. This is of modulus 1. Okay. So if you integrate it, that function, if you compute the F norm, e power nx, I mean it will be F bar. Mod F is 1. So it is just integral of 1 from 0 to 1. So the norm of this will be 1. If you take any two elements, okay, you can compute that the distance between them is square root 2. Okay. Just use the integral and R2. Okay. Square equal to 2. You compute the square. Okay. It will be 2. Write the definition, you compute the square, it will be Fn minus Fm bracket Fn minus Fm bar. You just compute, expand it and compute, you will get 2. So they have a fixed distance between them. So this cannot have a convergence subsequence. Okay. So this is not compact. The unit ball here is not compact. Okay. Ball of radius 1 around 0 is not compact. You can work it out. Okay, this is an exercise. Okay, what is next? Okay, let's formulate an equivalent definition of compact set. We have defined it using closed open sets. We will formulate using closed set. Okay, so this is the definition. Let F alpha, okay, alpha in some induction set is a collection of closed set. Okay, collection of closed set. Then you call it script F. Okay. Then script F has finite intersection property. Finite intersection property, which I call it as Fi. It has finite intersection property. If any finite subcollection, the intersection is non-empty. That's all. If F alpha 1 to F alpha n, if for any alpha 1 to F alpha n, intersection of F alpha I is not equal to empty. You have a collection of closed sets. You take any finite subcollection, their intersection is non-empty. Then we say that that collection has finite intersection property. That's all. Okay. Now we formulate an equivalent definition of compactness as follows. Which is just, you are just using the fact that the set is closed if and only if its complement is open. That's all. But we will use the negation of the statement. I mean, every open cover has a finite subcover. We will use the opposite statement. Okay. What is the opposite statement? Can anyone tell me? K is compact if and only if every open cover has a finite subcover. You formulate it using the negation. Suppose if every say it again. If every finite collection does not cover it, then the whole open set, whole collection cannot cover it, right? Every cover has a finite subcover. So every finite subcollection cannot cover it, then the whole collection cannot cover it, right? That's the equivalent definition, right? So that's the proposition. K is compact if then every collection of closed set, every collection F alpha with F alpha containing, this is maybe confusing for, let's take X equal to, X is compact, the whole thing is compact. And it's a, for K, you can restrict it and do that, okay? But that will be, we don't need it. We will write it for the whole set. Okay? X is compact. Then we don't need to write the containing and all. If F alpha in I closed set is a collection of closed sets with finite. Now, this is equivalent to for all X is compact, then for all F alpha, it's a collection of closed sets with finite intersection property. Okay, intersection of F alpha is also non-empty. Is it clear? Do one have to prove it? Okay, X is compact, then we have to prove that every, so F alpha, I assume it's a closed and all that, okay? Has FIP, satisfies finite intersection property. That means that is for all finite subcollection, finite sub F alpha 1 up to F alpha n, intersection of all these things is non-empty, which is equivalent to saying union of the complement F alpha I complement I equal to 1 to n is not equal to X, right? Intersection is non-empty, union of the complement is not the whole set. Okay? You just take complements everywhere, De Morgan's law. Okay? So this is 2. Okay, right? Then, of course, every finite subcollection does not cover, the whole set cannot cover, right? That's the compactness, equivalent definition. I just orally said. Yes. By compactness, union of alpha in I, alpha complement is also not equal to X. Okay. So this implies intersection of F alpha in I is non-empty. Okay. Done. So is the other way is also clear? Other way, suppose if it satisfies the finite intersection property. I mean, suppose every f alpha satisfying finite intersection property satisfies this. Okay, then it will satisfy this condition, right? Then otherwise exercise. Okay, same argument, nothing new. Okay, otherwise is exercise. You just argue it yourself. Same argument. There is really nothing. You are using the negation. I mean, the converse, the opposite state, not the opposite statement. The other statement of compactness. Okay? Equivalent definition of compactness. Just use that, you will get. Okay? So finite. So this is formulation of compactness using finite intersection property. Okay. Now there is something. So we know that closed and bounded does not imply compactness. So we want to get some sort of boundedness for compactness. So that is called totally boundedness. We will make the definition and then we will prove a proposition. Totally boundedness will imply boundedness, which is an exercise. You can take a bigger ball. Definition, X definition. So X is a metric space. So you can use it for a K contained in X is totally bounded. This is definition. Totally bounded if for given epsilon greater than 0, there exists x1 up to xn, finitely many of them, in K such that B of xi epsilon, should be true for all epsilon. Okay? For all epsilon, you should be able to get finitely many. Okay? So this is contained in, this contains K. Boundedness means there is one single big open ball which contains everything. Okay, for some fixed M. Here, given any epsilon, however small it is, okay, then you can cover this by this. And compactness will imply this immediately. You will see that. So exercise, very easy exercise. Totally bounded implies bounded. The other way is certainly not true because we have an example where something is bounded, it's not compact, but we will see that totally boundedness and closed will imply compactness if we prove this proposition. So let's take the whole set. Okay, X is metric space. Okay, the following are equivalent. Following are equivalent for XD. Okay, for a metric space XD, the following are equivalent. The first statement is X is compact. I'm taking the whole thing because I want to make this statement. X is complete and totally bounded. Okay. X is sequentially compact. As I said, we'll prove it again. That's all. These three statements are equivalent statements. You'll prove from here to here, 1 implies 2, 2 implies 3, 3 implies 1. Okay. So we assume compactness and we want to prove it's complete. Totally boundedness is clear. Okay, given epsilon greater than 0, you take Bx epsilon, okay, where x varies in x. This of course equal to x, right? It contains all x, so it should be x. So there should exist finitely many finite cover of this xn such that B of xi epsilon be equal to x. So totally bounded is clear. So we have to prove it's complete. Okay. Completeness also we have already proved actually. We have proved that it's sequentially compact. The sequentially compact means every convergent sequence has a I mean, every sequence has a convergent subsequence, we have proved. But if you have a Cauchy sequence, sorry, every sequence has a convergent subsequence, we have proved, if it is compact. If you have a Cauchy sequence, that will have a convergent subsequence. But a Cauchy sequence having a convergent subsequence will converge. You can prove. Okay, using triangle inequality, you can prove it. So because of that, we have already proved it. We are proving it again. Okay, we have from sequentially compactness, it will immediately follow. Okay, so we want to prove it's complete. So we haven't defined Cauchiness, but I hope all of you know that. Okay, what is Cauchy? I will write it again here. Okay, so Xn contained in X is Cauchy. That is, of course, for all that is given epsilon, for epsilon greater than 0, there exists a n such that the epsilon for all n. This is the definition, of course. Okay. Yeah. Close? No. No. It satisfies finite intersection property. There's nothing to do with cover.
The right side has nothing to do with
Which one?
the bracket of
It's all contained in X.
all of them.
That's why I'm not talking about subset of X. Then you have to say something contained in K something. I'm not making the statement. I mean, we don't want to do. I mean, if you want to consider a K, which is then you restrict the whole metric to that and work with that. Okay. I'm talking about whole space as compact. If its K is contained in X, which is compact, then I would change the definition of that. Okay. So what have we done? We have just defined quotient. Okay. So for K, so what do you have to prove? We have to find a convergence subsequence. We have a Cauchy sequence and we have to get a convergence subsequence. So for K in N, there exists a X and K. I mean, I'm choosing a subsequence. Okay. Yeah. And we have to use compactness, right? Okay. Such that D X and K X M is less than 1 by K for all M greater than Nk by Cauchiness. Okay, this is true. Okay. So we have used Cauchiness. Now B of I want to use finite intersection. I was just wondering what to use. Okay. Now take this B of, you can use open sets also, but this is easier. B of X and K 1 by K. Okay. By this I mean this is a closed ball. Okay. This is equal to all those X in X such that D of X and K is less than or equal to 1 by K. This is a closed ball. Okay. So you call it Fk, F and K. Okay. Then F and K has finite intersection property. Check, fine, proof. So if you take, I mean, F and K, what is F and K? F and K, is, I mean, Nk is increasing. Okay. So this F and K contains every xn after that. If you take finitely many of them, take the Nk, which is maximum of that. I mean, if you take finitely many of Nk1, Nk1 up to Nk, Nkn something, whatever, then you take the maximum of that, biggest number of that. Then that will contain, after that, whatever after that, xn after that, will be contained in all of them. Okay, so the intersection is infinite, right? Should I write it? If Fn K1, Fn Kn, okay, for Kn, let n is equal to maximum of this Nk1 up to Nkn. Okay, then this Fn, whatever that Fn, okay, that will be one number in that. That contains all xm, that has xm for all. Then Fn K I contains xm, has this xm for all m greater than that n, for all n. Let me correct it. So it's non-empty. That's what we want to show. This implies intersection of all those open balls, all those closed balls, 1 by k, k equal to 1 to n infinity, is non-empty. Like compactness, we are using compactness. Okay. Finite intersection, using the definition using finite intersection property, equivalent definition. Okay. So this is non-empty. Okay. But then this should contradict our. No. So this doesn't contradict. So we are not assuming that. So this is true. Now this intersection is non-empty. Let x is in this. P of x and k, 1 by k. There can be only one x. We will see it later. Something called Cantor intersection theorem. We will see it later again. Okay. Because the diameter is shrinking, there can be only one. Okay. And this x is in this. Okay. The claim is xn converges to x, but dxxn is less than or equal to dxxnk, okay, plus dxnk n. Okay. So for all n greater than nk, x is in all bx and k. Okay, so this will be less than 1 by k for all k. Okay, doesn't matter. Okay, and I mean, as this will be very close. So this is less than epsilon or 2 epsilon, whatever. I mean, 2 by k. This goes to 0. 2 by k, which goes to 0. So this is the limit. Okay, so xn converges to x. So every Cauchy sequence converges. Okay. Look at it. If you have a doubt, you ask me. We started with the Cauchy sequence. We use the finite intersection equivalent definition using finite intersection property. Okay. Then from that we got a limit. So it's complete and totally bound. So some set is, some metric space is compact if and only if it is complete and totally bound. So now we assume completeness and totally boundedness, and we want to prove it's sequentially compact.
We have an example of a set that's bounded but not totally.
Yes. The whatever we discussed, the set in L1 unit ball in any infinite dimension. In finite dimension, it's not true. Okay. You take discrete metric space and work with that. Any infinite surface. This distance between anything is 1. Or you can, given any metric, you can get equivalent metric, bounded metric, work with that. Okay. In discrete metric space, only finite sets are compact. Okay. The singleton is open. But they are not useful. I mean, they're just mathematical objects, but useful objects are this non-linear space and all that. So they are in infinite dimensional. Finite dimensional is true. We will prove it after this. Finite dimensional closed and bounded implies compactness. 2 implies 3. So we are assuming it's complete and totally bounded. Then we want to prove it's sequentially compact. Okay. To prove sequentially compact, let Xn contained in X be any sequence. We have to produce a subsequence of this, which is convergent. Okay. So let k equal to 1. We start with 1. Then B there exists x1 up to xn. So we have x already. So y1 up to yn. Okay. N or m doesn't matter. M in x such that B of yi 1 union I equal to 1 to m equal to x. Totally bounded. Okay. Using totally bounded, this is true. Okay. Now this xm, I mean, this is an infinite sequence. Okay. If it is finite sequence, then there is no problem. You can, I mean, it's an infinite set. If you collect this set, this is an infinite set. Okay. Assume this is set, not sequence. N in n is infinite. If it is finite, of course, you can find a constant. You will want something will some element will repeat infinitely. You get a constant sequence, which is conventional. Okay. So this is an infinite set. Okay. So this is there are finitely many sets. Okay. Then infinitely many of these actions should be in one of these balls, right? Right. I mean, if it is only finite intersection, there will be totally finitely many of them. Okay. So that's not true. So there exists infinite subset of this xn, this set. I'm assuming this set is infinite. Okay. Contained in B of y, B of some y. I want to call this as y1. Okay. Let's assume without loss of generality that is the y1. Okay. You can start with any y1. Okay. y1. No, 1 by 1 y1. Okay. I mean, it's going to be in one of them. You can shuffle it and you call y1 being the set which contains infinitely many of them. Okay. Okay. Now you consider a subsequence of this which intersects, I mean, let me call this set E. Okay. E intersection B of y1 1 is infinite. Any subset of a totally bounded set is also totally bounded. That's clear, no? Okay. Now choose some y2. I mean, use the same argument. Okay. This can also be bound. This can also be covered by finitely many open balls. So now choose y2 in B of y1 1 such that E intersection B of y2 1 by 2, okay, is infinite. Right? I'm using the same argument. Continuing this, okay, choose yn, such that E is that sequence set. Okay, this sequence. You can work with any infinite set, but I have to use 2 arguments again. So I'm just taking this set. Okay. It's equivalent. If you have any infinite set, you can form a sequence. Infinite sequence. Okay. So such that E intersection that all those, I mean, that, I mean, E intersect with, I mean, this is a decreasing sequence, okay? P of yn 1 by n is infinite. Now the point is, so what did we assume? No, now this sequence yn is Cauchy, right? Yn is in the previous, I mean, d of yn ym, assume that m is greater than n. So this is less than 1 by n, right? Okay, and which will, this m is greater than n or something. So this is Cauchy. Because of this is Cauchy. Okay. Now this yn is Cauchy, so directly a y in x such that yn converges to y because it's complete. We have used totally boundedness, we have used completeness. Okay. Now choose x and k in this set. E intersection b of yn 1 by n. Okay. Because, I mean, right? You can choose a subsequence so that it is in this, right? For each case, maybe the indexing may be a bit confusing because it is y, okay, b k 1 by. Now it's clear. That's okay. Okay. This is yn. Okay. Now this x and k should also converge to y. Okay. D of x and k y is less than or equal to d of x and k yk plus d of yk y. Okay, which is less than 2 by k or whatever. Okay, it goes to 0. So we have proved sequentially compact. I'll pause for a minute. If you have a doubt, you can ask me. What we did is the following. We just work with an infinite set. Okay, we want to get a subsequence in that infinite set which converges to something. We are proving that every infinite set has a limit point. Okay, that's what we are doing. Instead, I'm taking the sequence and proving that. Okay, so you take an infinite set E. Okay, then this finitely many open balls covers X. So you one of the open balls with intersect with the infinite intersection should have infinite. So take that open ball. Okay. Now that is also totally bounded. So you can cover with the 1 by 2 with that 1 by 2 radius. Okay. Then you take one of them which intersects with infinitely many. Okay. Do this and you get this kind of open balls, and all those centers which is with shrinking open balls should be Cauchy. Because distance between they are contained in one is contained in the other. Okay, so the distance between them should go to 0. Okay, so it's Cauchy. Now we are using the completeness to prove that completeness to assert that yn converges to y. And this now you choose some x and k because the intersection is there. You can choose some x and k that should also converge to y by triangle inequality. That's all. Okay, triangle inequality and proof. So every infinite set has a convergent sequence. Okay? Every infinite set has a limit point. That's what it means. Okay. Now we want to prove the final one. Three implies one. So we want to assume it is sequentially compact, then we want to prove it's actually compact. Okay. To prove compactness. Okay. So we start with, we use open open cover definition. Okay. Let X is equal to union of alpha and I U alpha. Okay, this is open. To have an open cover, we want to get a finite subcover. Okay. Okay. So for X in X, let Rx. For X in X, there exists a R greater than 0 such that BXR X is in X, X is covered by U alpha, so X has to be in one of those U alpha that is open. So BXR is contained in U alpha or some alpha. Okay. Alpha. Okay. Now you define Rx, a number, which is equal to supremum of all R such that BXR is contained in U alpha for some alpha. Okay. There X is 1. Now you take the supremum over all, which is positive. Okay. Since it is bounded, compactors are bounded, this cannot be infinite. Right? Okay. So since X is bounded, Rx is a real number. Okay. It's not infinity. Okay. Now I take the infimum of all over alpha. Now let epsilon equal to infimum of all Rx, X in X. Okay. Claim is this epsilon is not equal to 0. Greater than 0. Maybe epsilon not. Epsilon is varying, epsilon not. So that it's a constant. Okay. So we have an Rx for each X. We took the supremum of that for each X and call it Rx. Okay. Now we are taking the infimum over the whole set. Okay. Now this is what is called Lebesgue number of the cover or something. Okay. I'm not using the definition because I will not be using it anymore. So, okay. So we have an epsilon naught, which is okay. So suppose if it is equal to 0, then we want to get a contradiction. Yeah. Huh? Because you have a big open ball BXR, which is equal to X. That's all. You cannot. No, which is contained in U alpha. If it's all bounded set, I mean, by the definition, okay. You want to change the definition, that's all. I mean, yeah, for a bigger R also it is true. That's what you are saying. You have to change the definition a little bit. For all, how do you change it? I mean, if it is U alpha is if it is non-empty, I mean, if it is not singleton U alpha, if it's not just X, okay, after some time this will go out. Okay, so assume that is an infinite collection. If it is a finite collection, there's no point. Okay, so this is an infinite collection. I is infinite. Then it works. Okay, because it will go out after some time. If you have a U alpha as a proper subset, then BXR has to intersect with the complement at some point. So this will not be satisfied. Assume I is infinite. If it is finite, there is nothing to prove. We want to get a finite subcover, so it's okay. Okay, so that's all. It's just being precise. Okay, that's all. So assume I is infinite, then it works. Okay. The X is a finite R, finite Rx. Okay. Now we want to use what? We want to use the sequentially compactness to prove that epsilon naught is greater than 0. Okay. Suppose epsilon naught equal to 0, that means that infimum is equal to 0. Okay. That is B of X or X. Direct is sorry. Direct is Xn contained in X such that Rn, Rxn goes to 0. Okay, that's what it means. That's what it means. Infimum 0 means direct is, these are all number for Xn. Direct is a Rxn goes to 0. That is given by Rx. So Rxn goes to 0. Okay. Okay. Now direct is a subsequence by sequentially compactness. Okay. Sequentially compact implies direct is a subsequence X and K such that X and K converges to some X. Okay. Now X is in some U alpha. Okay. So there exists a B, X, R contained in U alpha for some R greater than 0. Okay. Now, so now X, consider this X and K, and X and K converges to X. Okay. So D of X and K X is less than, say, I mean, it will be in X less than R for some, there exists a K, there exists a N, such that the N for all N greater than that N. After some N, dx and kx is less than R, right? So this implies D, I mean, so if Y is in dx and k, because I mean, I claim that dx and k are by 2 or something is contained in U alpha. Dx and k, this is just the conversion. X and k converges to x. So this is true. X is in some U alpha, so this is true. Okay. Now this open ball contains this x and k after some time. That's what it says, after some time. Okay. Now this dx and k r by 2 will be completely contained in this. Right? Now dx and k. Now if dy x and k is less than r by 2, maybe this here also r by 2 I need, maybe r by 2 here. Let's see. Then d of y x is less than or equal to d of y x and k plus d of x and k. Okay. Now this is maybe call this r by 2. So this is less than r. Okay. So this implies b of x and k r by 2, okay, is contained in b of xr, which is contained in U alpha. That's what I will just return it as another way of writing it. But this will imply r of this x and k is greater than this r by 2. That's the definition of R, right? Which is the supremum of all these things. Okay, I will write it here. I don't want to go to that board. This implies R of n x and k is greater than R by 2. So for a fixed R, okay, so R x and k cannot converge to 0. Okay. Let me go through it again. I'm taking a open cover. I want to get a finite subcover. Okay, I mean, I haven't got the finite sub. I want to get a finite subcover. Before that, I'm trying to, I got an Rx for each X, and I'm taking the infimum over all such Rx, and the claim I have proved is this epsilon naught is greater than 0. Okay. So to prove that epsilon naught is greater than 0, suppose if it is equal to 0, then there exists a sequence such that this goes to 0. Okay. This Rxn goes to 0, but Xn will have a convergent subsequence that will have a limit X, but that has to be in one of the open balls. So Bxr is contained in one of the open balls. Okay. Now Bx R by, I mean, Bx R by 2 or whatever, Bx R is contained in one of the open ball, then R by 3, whatever, doesn't matter. Okay. Then you can find an open ball around this Bx and K that is contained in that open ball, which is contained in that. By the definition, this Rx and K cannot go to 0. That's what I want to show. Okay. Okay. Think about it. So epsilon naught is greater than 0. Okay. Okay. Now we get a finite subproblem. So we have an epsilon naught. Then, so from that, what we conclude is we have proved the following. We have proved that epsilon naught is strictly greater than 0. We have proved that for any x in x, there exists alpha, okay, such that b of x epsilon naught is contained in u alpha or some other. Okay. This is what we have proved. Okay. Maybe you can take delta less than, I mean, that is an infimum. So maybe you can take it less than that if you want. We have proved that for delta less than epsilon naught, okay, if you want it to be precise. Okay. I think it's okay. Anyway, it's okay. Okay. This is true. Okay. Now we want to say that there are finitely many of these things cover the x. Okay. So what will it contradict? Choose some x1 in x. Okay. And choose x2 in x minus b of x1, that delta. And epsilon naught will not work, but let me use delta. Okay. Delta. Choose by this, you choose xn in x minus union of b of xi, I equal to 1 to n minus 1 delta. Something which is not in this union and this. Okay. But then this cannot happen. This has to stop at a finite level. Suppose you can choose, suppose xn. I mean, you can choose, suppose you can choose infinitely many. Suppose there exists infinitely many such xn. Then the xn's are separated by a distance delta, right? Okay. D xn xm is greater than delta, cannot have a subsequence. Okay. It cannot have a convergent subsequence, right? Because they are separated by delta. So this has to stop at a finite stage. Okay. So there exists. So from that, this we conclude there exists x1 up to xn such that b of xi union of I equal to 1 to n, right? That delta equal to x. Where this now there exists alpha I such that b of xi delta, we have already seen this, u alpha I. Okay. Clearly, union of u alpha I. B of xi delta equal to x. So x is compact. That's all. Done. Yeah, I think I'll stop.